Welcome to the class of data science for non-life insurance. And today we're going to talk about the rise of the machine learning basics for actuarial work. So the goal, as I already mentioned, is to introduce a few concepts, a few terms, some terminology that we need to understand before we will be able to dive more deeply into the machine learning techniques that will follow in the next classes, right? So let us start with acknowledging a few books that I used to put these sheets together. So every now and then you'll recognize a figure or a table or something that is taken from one of these sources. So you can have a look at these books to read more, to find out more about these techniques and these concepts. All right, so let me start with this picture to introduce a few concepts and some terms which we probably already mentioned in the class, but it's good to repeat them at this point. So here you see, if you look at the machine learning landscape, if you want, or the more traditional, more classic machine learning landscape, then you'll first see the distinction between supervised learning and unsupervised learning. So we already discussed that. With supervised learning, there is a particular target or a particular label that you're trying to model and to predict. So think, for instance, about the number of claims reported by a policyholder. If you look at the unsupervised techniques, then there is no particular label or target present in your data. So the author of, or the creator of this graph describes it as the data is not labeled in any way. So we basically only have a vector of features available for our records in the data set. Now, if you look within the branch here of supervised learning methods, then people usually make the distinction between classification and regression. So that is about the structure of or the nature of your target variable. So with regression, we're looking at a numeric target variable. Think about the number of claims reported, think about the severity of claims or something like that. With classification, we're trying to predict categories. Could be 0, 1, but could also be more than 2 categories that you try to predict. Okay, so it's important to have these distinctions in mind when you consider the next classes. Within the domain of unsupervised learning, we could think about clustering methods. We already encountered a first clustering method when we were clustering these postal code areas on the map of Belgium in our workshop on building a tariff. So modeling the frequency of claims reported. There we already used a few of these clustering techniques. You could also think about dimension reduction. Think PCA, think autoencoders in neural networks, or you could look into what is here called association methods. I'm not so familiar with those, but okay, apparently that's a different category of techniques to be distinguished here. So personally, I would really recommend you to have a look at the website where I got this picture from. So this is a beautifully illustrated website on machine learning techniques. It's called Machine Learning for Everyone in Simple Words with Real World Examples, yes again. So you can find a lot of visualizations on this website like the one I'm showing here. Yeah? So for us today, the distinction between supervised and unsupervised is important, and then the distinction between classification and regression will also come back today. Okay, so what's in a name? We already talked about these different terminologies which are out there. So as a quick recap, I will denote with machine learning techniques, a whole bunch of algorithms to learn from data. If I talk about statistical learning, then I will rather think about statistical models and the assessment of uncertainty. So think about linear regression, think about generalized linear regression, generalized additive modeling. That would be examples of statistical learning methods as a subset of machine learning techniques. And then data science more in general, that can refer to any mathematical technique or statistical technique to extract knowledge from data. So that's a slight typo here. We already mentioned the three first books of which you see the cover over here as references for our course. And today I want to add these two, which are more oriented towards machine learning, but which are also excellent resources to study machine learning techniques. You see the book by Boomke and Greenwell on hands-on machine learning with R. You see the book on interpretable machine learning by Christoph Molnar. So these are resources that I will cover during the next classes. Yeah, so keep those in mind as references. So today I'm going to talk a lot about supervised learning. I will also refer to it as a predictive modeling. So that means I've got a specific response, outcome, or target Y in mind. I've got P different predictors or features, X1 up to XP, and I assume that I can express the Y as a function, F, an unknown function, F of these features, plus some random error term, the epsilon. Yeah, so that's the setting I have in mind. The F is some fixed but unknown function of the predictors, the features. The epsilon is some random error term, okay? And I will see different techniques to try to capture this or to try to estimate this F. We already discussed a few of them, the generalized linear models, the generalized additive models, and we see way more such techniques, particularly from the field of machine learning in the next classes. So what is this F doing? We can say that the F is representing or capturing the systematic information that X provides about Y. So we could say this is the signal we're trying to capture. And these predictive modeling techniques, they refer then to a broad set of possible strategies to estimate this F from a given data set, right? You also have the epsilon here. So that's the part which we cannot capture with our model F. So we'll say that the noise, F is the signal, epsilon is the noise in this particular setting, right? Now, if you look at why would we be interested in estimating this F, then we'll make the distinction between prediction on the one hand and statistical inference or inference on the other hand, right? And I would like to show that here with this picture as well. So if you look at this data science spectrum or continuum, then we would say, well, traditional statistics, also referred to as white box modeling or statistical learning, will typically be interested a lot in statistical inference, so in drawing inference from the model. Think about trying to identify causal effects, trying to find the correct model, emphasis on measuring uncertainty, doing hypothesis testing, etc. But on the other hand, we could also look at these machine learning techniques, also referred to as black box modeling, where our emphasis will be more on the quality of predictions, so on delivering predictions with a high accuracy, as accurate as we can build them from the data that are available, right? So these are two different or two goals, which are traditionally listed as reasons why we try to model this function F. So let's dive a bit more into that. So when the focus is on prediction, we're interested in delivering a prediction for the target variable y. I will denote that here as y hat, which is the estimated function, the f hat. So that's the model that we build from the data, the model that we calibrate from the data. F hat evaluated in input variables x, right? So f hat is our estimate for f, and if our only goal is prediction, then we could treat this f as a black box, That's a bit gechargeerd. That's a bit of an overstatement, I would say, a strong statement. But in principle, you could say if my only interest is in delivering accurate predictions, I don't care too much about getting insights, about getting an understanding of this f hat. I could treat it as a black box, right? And what then matters is that we look at the accuracy of the y hat as a prediction for y. And we'll see that if you decompose this squared error, where you compare the original, the true y, with the prediction that we deliver for this y, the y hat, if we look at the expected squared difference between these two, then we can decompose that squared error in the following way. So what I'm doing here is I replace the y with fx plus epsilon, as we've seen before, and I replace the y hat with this f hat evaluated in x. And then I'm going to work with this term, so with this squared term, and I'm going to take the expected value of this thing, right? And then you'll see in the end that we can write this as f evaluated in x minus f hat evaluated in x squared plus the variance of the noise term epsilon, right? Now, some people will say, yeah, you're forgetting a particular term here. That's the variability of the f hat. We'll bring that in later. So for now, at this point in the lecture, we will assume that both the x and the f hat are given, so that these are not random variables, and that's the reason why I leave out the variability of this f hat. I will come back to that. I will deliver a more correct expression for this squared difference later on. Yeah. So the point here is that I will recognize here a squared bias term, which I will call at this point a reducible error. And then I have here the variability of my noise terms, and that's an irreducible component in this expression. So what we mean with that, with the reducible error, is, well, this f hat, it's a model, so it will never be a perfect estimate for f, but potentially I can increase the accuracy of f hat as an estimator for the unknown f. So that means if I go for a more complex technique, yeah, then I will be able to reduce this reducible error by building a more complex model. On the other hand, if I look here at the irreducible error, then we'll see, well, my original target y, that's also a function of epsilon. This cannot be predicted using the available features, so I won't be able to reduce this part, right? So keep that in mind. We'll see that coming back. So you have a bias term here, a reducible error term, you have an irreducible part, and at this point we'll say, okay, if I build a more complex model, then I will be able to reduce this part in the error by looking at a more complex technique. So we'll see that mechanism come into play later on in this technique, in this class, right? So Said says there should be an expectation for the first part in the equation. Well, at this point, I don't have that because I'll assume that the f hat is given and the f is also given. So there is no random variable in this expression. So there is no need to write an expected value over here. But I will come up with a more accurate expression later on. So here, this is just to gain some first insights. Right? So the reason that there is no expectation is because I assume the f to be given, to be known, and I assume that the f hat is known as well. Right? So that was the goal for prediction. So then we care about getting this squared difference between the true target and the estimate for our target as small as possible. If we look at the goal of delivering inference, then we care about how is the y changing when the input features are changing, right? So then we want to understand the relation between x and y. And we don't want to treat the F hat, the model that we're building, we don't want to treat that as a black box. We want to get insights in what this F hat is doing. We want to know its exact form, or at least gain some useful insights from this model that we built, right? So questions that fit into this goal of getting inference and understanding the F hat would be about, yeah, which predictors are associated with the response. So this is the question of variable selection, if you want. What is the relationship between the response and each of the predictors? Can this relationship be summarized, for instance, with a linear equation, like in a regression model? Should it be more complicated? Should it be a polynomial expression? Should it be a nonlinear expression, etc., etc.? Yeah? So that's the kind of questions which fit within this goal of inference. So at this point, we put these two goals quite separately next to each other. We said either you go for predictive accuracy, either you go for inference, and that will sort of drive the kind of models that you want to use for the particular problem that you are facing. But nowadays, and we'll see that later in the course, nowadays there's of course a lot of emphasis also on building interpretable machine learning models. So nowadays you will see that even if I care about prediction, then I will still want to understand how my predictive models are working, what is the relation between my target variable and some input variables. So nowadays we'll also see that tools and principles are being constructed to think about the interpretability, the accountability of the predictive models that I'm constructing, right? So it's a continuum from from inference to predictive accuracy, but you'll see that these two goals are being blended more and more, and especially in insurance applications, that's highly relevant because we operate in a regulated business, so we don't want to deliver in general black box models, but we want to understand with the appropriate tools what these models are doing with our data. All right. Any questions on that? Anything we wish to add? So we started with our spectrum. So we started with these supervised, unsupervised classification, regression. We talked about predictive accuracy and inference. And now we want to say a few words about how to express the model accuracy. So the accuracy of a model that we're building or that we're investigating. So first of all, an important claim is there is no free lunch in statistics or in machine learning. So that means that in general, we cannot find a single method or a single algorithm or a single technique that dominates all the others over all possible data sets, right? So that means that for each data set we want to consider, we will be able to look at different kinds of models, different kinds of techniques, and selecting the best approach is of course a challenging task. It's a challenging part of performing the machine learning in practice. And what this part of the presentation is about is how can we set up some useful tools in order to express or to measure somehow how good a model is performing in predicting a given target. Right, so this is about evaluating the performance of a learning method on given data. So we want to evaluate, we want to express or measure how well our predictions match our observed data. So we want to quantify the extent to which our predicted target or our predicted response for a given observation is close to the true response value. And now typically if you look at a regression setting, then you will see that a lot of these textbooks that I mentioned earlier on, that they will use the mean squared error as the way to measure the accuracy of our prediction. So what we're going to do here is let n be the number of observations, either in our training set or in our test set. And what we're going to measure is then the square difference between the target y and the prediction that we deliver for this y. So you could write it here with an f hat if you prefer that. And my notation here, so the theta refers to, let's say, either the regression parameters or the tuning parameters that my model f is going to use. And I'm evaluating my f in the available features captured with the vector x or xi, the available features for observation. So this is one of the ways that I could use to express the accuracy of my model. Yeah, I denote that here with an L. This L refers to the loss. So we also call that the loss function that we want to use to evaluate our model, but also to train our model. Now, of course, if you look at different settings, so not necessarily regression, or not necessarily regression with a numeric outcome, you could also think about other loss functions. And that will be very important throughout our course because we want to use the loss functions that are relevant for the actuarial applications that we have in mind. Yeah? So we'll come back to that later on when we're actually going to do, for instance, tree-based learning for claim counts or for claim severities, or when we're going to do a neural network for claim frequencies and so on. But here you already see a couple of examples of things that could be useful at this point. Yeah? So what I could do is, instead of looking at the mean squared error, I could also look at the residual sum of squares. That's of course super related. The only difference is that I'm not dividing here by the number of observations in the data set. I could also look at the log likelihood. So here I take the log of the density that I'm willing to assume evaluated in my target variable, or the log of the probability function in case I'm working with discrete data that I wish to use. If I look at a classification problem, think about a 0-1 problem, where the y, let's say, denotes outcome 1, and then 1 minus y denotes the alternative, where the y denotes the outcome that my target is taking, so it's either 0 or 1, and p the probability that my outcome is going to take p the probability of seeing outcome 1 in this setting, then I can construct what is called the cross entropy measure, or what you recognize here is the likelihood, of course, of a Bernoulli model. I put a minus in front to make it the minus likelihood or log likelihood, so that I can target the minimization of this particular measure, right? So the important thing to keep in mind here is that you can have different loss functions which are suitable for different kind of problems that we want to consider. And we'll see more of these later on. We're going to work as well with the Poisson deviance, for instance, as the loss function in when building, for instance, tree-based models for claim frequencies, and so on and so forth. So the message is here that you have to pick a loss function in order to express the accuracy of your model, but this loss function should be suitable for the actual problem, the kind of target variable that you're trying to model. Okay. Now, how are we going to express this accuracy? So say that we fit our model on a given data set. So here I have n observations in my data set. The y is the target variable, and this x denotes the vector of input features. So say that I fit our model on this training data set, and I'll get the estimated model f hat, right? Then we're not really interested in measuring or expressing whether this f hat evaluated in x will be close to the target variable y for the training data, right? We're interested in seeing how well the f hat performs as an approximation for the outcome or the associated outcome y, when this x naught and this y naught is an unseen test observation that is not used to train the model. Yeah? So the message here is we actually want to make this distinction between training data on the one hand and new test data on the other hand. And what is interesting, what is our interest when establishing a good predictive model is to see how this f hat that we captured, that we built on a given training data set, how that generalizes to a new data set, a new test set, right? So we compute the average test error, or the loss function evaluated over the test data, and we want to select a model for which this test error is small. So we're going to look at the test mean squared error, or the test loss function that we prefer, and we're going to compare different model settings, and we're going to compare different models based on their performance on this test set, right? So here we come to an important term. So when are you going to say that a model is then overfitting? Well, a model is overfitting if you're able to construct a very small training error, or let's say a small training mean squared error, or more general, a small value of your loss function over the training data. But when you apply the same model to a new data set, you will realize a large value of your test mean squared error, or a large value of the loss function that you want to use when it is evaluated in your test set. So that is the phenomenon of overfitting. So that's something we want to avoid, obviously. So when a model is overfitting, it means that our learning procedure is working too hard to find patterns in the training data. So it's capable of bringing or of making this loss function evaluated in the training data set. It's capable of making that very small, but when you apply it to new data, then a large value of the loss function will result. So we see that we're picking up the noise in our data and not necessarily the signal, right? So we pick up patterns in the training data then that are caused by random chance. So we pick up the noise and not necessarily the signal that is present in our data. So the test loss function, or the test mean squared error, will then be large because the patterns that we suppose to be present in the training data are not generalizable to the new data. They are not present in the test data. Okay. So what you see here is that when you get a bunch of data, or a bucket of data at your disposal, well, at this point, we're going to make the distinction between setting up part of the data to train your model and part of the data to evaluate the performance of your model, or to test the performance of your model on new observations. Yeah. So at this point, the distinction between this holdout methods, the train, validate, test approach, or the cross-validation approach, that's not relevant yet. So I'm going to explain that later on today. But at this point, I want to make the distinction between using training data to calibrate your models, to figure out which parameter settings are relevant, etc. And then you're going to use this model that you built on the training data, you're going to use it to evaluate its performance on this test data. And what is important here is this lock that you see. So the little icon or picture that you see over here. So we're going to put this test set under lock. We're going to use it by no means in the construction phase of our model. So it's really a part of the data that we're going to set aside, and we're only going to use that to evaluate the performance of the models that we calibrated. Okay. So if we look at the shape that we see in these test, let's say, mean squared error curves, then then we're typically going to recognize a U shape, and we're going to see a few examples of that further on, and practice a little bit with recognizing the difference between overfitting, underfitting, and appropriate fitting, let's say. So the U shape that you see in your test mean squared error curves, that's going to be the result of two competing properties of statistical learning methods. And we can see that by looking into the expression for the expected test mean squared error. So we're going to look at the expected value of the difference between Y naught, a new observation, and the prediction that we construct for this y naught, for this y naught, that's the f hat evaluated in x naught. So we're going to look at the expected square difference between these two. And then if you do the expression that we already encountered earlier on, when we talked about the reducible error versus the irreducible error. So if you derive this expression in full detail, then you're going to recognize that you're essentially looking at an expression consisting of the variability of my f hat, the bias of my f hat squared, and the variability of my noise term. So we recognize a bias, which is expressing the difference between the f evaluated in x naught and the expected value of the f hat we constructed evaluated in x naught. So this bias term squared. We recognize the variability of the predictive model that we constructed, and we recognize the variability of our noise term. So there is a lot in here, and you can carefully write that down. Let me put that in a separate document and upload it on Toledo so that you can have a look at that later on yourself. But this is the decomposition that we recognize from mathematical statistics if we look at this test mean squared error. So to minimize the expected test error, what you will need is low variance as well as low bias in order to make this expression small, because you know that the variability of the epsilon, that's something you cannot work on with your predictive model. That's the irreducible error. So that is a given. You cannot improve on that by constructing a model f hat. Yeah. So to get a small value here, you need low variance, you'll need low bias at the same time. And we know that this test mean squared error, it can never go below the variability of the epsilon, the irreducible error. Yeah? But these two first components, that's something we can work on by playing around with the level of complexity and flexibility of our predictive model. Yeah. So first, some considerations before we dive into a few examples. So what do we mean with this variance and bias of a statistical learning method? So we see that both matter in the expression for the test mean squared error, but what is it exactly capturing? And so how would we interpret this variability? How would we interpret this bias? So let us first look into the variance. So this variance of f hat is expressing how much the f hat would change if we would calibrate it on a different training data set. So typically you'll see that if you have very flexible methods, yeah, so think about a gradient boosting or a neural network or something, if you would calibrate the same model on a new training, on a different training data set, then the model could quite change a lot. So that's a method with high variability, right? So that's the second bullet here. If you use a method with a high variability, small changes in your training data could result in large changes in the f hat. In general, as I already mentioned, more flexible statistical methods will have higher variability, right? If we look into the bias term, so that is the error that you introduce by approximating a real-life problem with a model, right? So that is the difference between the true f and the expected value of my f hat, and then we get this bias term squared in our expression, right? So if the true f is substantially nonlinear, for example, then no matter how many training observations you have, if you're gonna construct for the f hat a linear model, yeah, then you will never be able to get close to the true f. So you will always have a significant or a quite substantial amount of bias in this expression, okay? So if you take a true f substantially nonlinear, if you take for the f hat a linear regression model, then this bias term will always be substantial, for example, right? In general, if you do more complex models, yeah, then you'll get more flexibility for the f hat, so then you will be able to approximate your unknown f in a better way, you will be able to reduce the bias term. And here I give two examples. So I just simulated these, the variable x, I simulated the outcome y, and I assumed some nonlinear relation between this y and this x, right? So I generated data from a given model, and then I'm going to fit two different models. So in this case, I took some kind of polynomial fit, if I remember well. So you'll see here that this is quite a crude approximation of what the data really look like, so what the model was really about. So this is a model where the bias is quite substantial. Okay, it's a model that doesn't have a lot of variability, because if I would fit this model to new data, the model will still look quite similar. But on the other hand, in the second picture over here, I generated the same data, but now I fit a k nearest neighbor regression model, where I took a small value for k. And we're going to talk about that more later on today. But what I see here is that I get a very variable model fit. So if I would rerun the model on a new data set generated, then I could get quite a different result. So this is a model with a high variability, although it is quite capable of getting close to what the observed data are in the training data. Okay, so you have this trade-off between bias and variance. And if you want to make the test error or the test loss function, if you want to make that small, then you'll have to find a model that is both leading to small variability as well as a small value for your bias. Yeah. So in general, as we already discussed, if we have more flexible models, then variance will increase, bias will decrease, but the relative rate of change determines how this test mean squared error will look like. So let's make that a bit more specific by looking into some examples. And in these examples, you will recognize the following curve in general. So this is an important visualization. It's taken from the Introduction to Statistical Learning book that I mentioned on the first sheet in this presentation. So what I have here on my x-axis is the model complexity, ranging from low complexity to high complexity. So here I find at the left side of my x-axis, I find models like a linear regression model or a lasso regression or a generalized linear model. So they are low in complexity, and so they are very interpretable and simple to express and to estimate. Here I find models with a high level of complexity. So here I find stuff like the gradient boosting or the neural networks, etc. Here on the y-axis, we express the prediction error. So that is our error as measured on a test set, on a new set of data. And if we look at the blue curve, which is, no, sorry, I express it wrong. So here we express the prediction error. So this is our, think about a mean squared error or think about a loss function. And now we're gonna evaluate this prediction error both on our training data as well as on our test data, right? So if we look at the training data in blue, then we see that we are capable of pushing this prediction error evaluated on the training data. We're able to push this prediction error to 0 if we build more and more complex models, right? Because that means you've got the data. So if you start building more and more complex models, in the end, you could just interpolate your data. You can just reproduce the given training data. So you will always be able to push this error evaluated on the training data to 0. But what you will see happening then is that if you evaluate the same model, if you use it to predict new data, test data, then you will recognize this famous U shape in the prediction error evaluated on the test sample. So you'll see that from a given point on, from a given inflection point on, the error evaluated on the test data will start increasing again. So when do we say that we're overfitting? Well, we're overfitting as soon as we enter this area. We're overfitting if we construct a model that is capable of pushing the training error to 0, but when evaluated on new data set, on new data, this model will reveal prediction errors that start to rise again. So that's an indication of overfitting from here on, right? This here is an indication of underfitting, right? Because you're here working with models which are too simple, which have errors evaluated on the test set that you can still decrease by increasing the level of complexity. So where do we find the appropriate level of complexity? So that's somewhere in this area. So you can either go for the model that actually minimizes the error evaluated on the test set, or you can apply rules of thumb like the one standard error rule. We'll explain that at the end of today's course. Yeah, but it's important to look at curves like this to define, to pick the parameters in your model on the one hand, but also to compare models amongst each other when looking for an appropriate specification, an appropriate model to model the data that are given. And do remember this test set, this is a part of our data that we put under lock and that we by no means touch during the model building phase of our exercise. Complexity, model complexity on the x-axis, that you have prediction error on the y-axis, and then want to compare the performance of different models, in this case expressed by different levels of complexity on both the training data and the test data. And you want to recognize when is a model underfitting, when is it overfitting, and when is it fitting appropriately, let's say, right? So we're going to do this by looking at a few examples, and we're going to start with regression type of examples. So let's say that we would generate data from the following specification. So we've got y is f of x plus epsilon, and we're going to simulate from a given curve or a given true f, right? And in the pictures that you will see appearing on the screen, this true f is going to be put in black. Sorry for that, right? And what we're going to do is we're going to fit three different models for this true f. We're going to do a linear regression, which is pictured here in orange. We're going to do a blue curve, which is a smoothing spline, and we're going to do a green curve, which is another smoothing spline, right? But with a different level of complexity compared to the blue one, right? So as such, we construct three different estimates for the model F, right? With increasing level of complexity. So the whole idea is pictured in here. So we know that there is this true f in black. So that's the true signal, if you want, or trend in our data. So we've got one input variable x, and we've got the outcomes y, which are then generated from this model. Y is f of x plus epsilon. So the f are my targets. They're simulated from this known model where the true f is visualized with the black curve. Then I fit these three models. So my orange model is just a linear regression of y versus x. My blue curve is a smoothing spline, and my green curve is another smoothing spline, but the green is more complex, so more wiggly than the blue one. Now, if I evaluate these three models on the training data, and the training data are the dots that you see in the picture here, over here, right? If I evaluate my mean squared error with the three models on the simulated training data, then I'll get their performance like this, right? So what I see here is, of course, that the linear model is leading to the highest prediction error, in this case mean squared error on the training data, and that this performance improves over the when I increase the complexity of my model. So I can push this training error to 0 if I make the model more complex and complex, right? But if I evaluate these 3 models on new data, so test data, which I can also generate from the known model here, then I'll get a performance like this. So here I recognize this U shape, which of which the behavior in this U shape is driven by this trade-off between the variability and the bias of the models that I constructed. So my question for you is now, which model would you prefer here? Would you prefer the orange one, the blue one, or the green one? So I cannot immediately find how to put a poll in this Zoom session, but those who want to share their thoughts, just raise your hand if you want to answer, or just type in the chat which model you would prefer, orange, blue, or green. Gives me a second to be able to taste my coffee. But what would you prefer, orange, blue, or green? Very good. So many students prefer the blue one. Anyone willing to explain why you prefer the blue one? Not by typing, but maybe just by unmuting the microphone or raising your hand. Yeah, so Bavo says it fits the data, but it does not overfit. And the reason why we see that it's not overfitting is because it's in the, let's say, the minimal zone, the minimal area of my test mean squared error. Whereas if I go for the green smoother, then I will see that my test error is increasing again over here. So this is not a good fit because it is capable of driving the training error to 0, but when I apply this green smoother to new data, I will see that it's really that the trends that it picked up in the training data are not generalizable, they are not transferable to the test data, as I can see here, because my test error is increasing again. Okay, anyone who can explain what this dashed line would mean? Any ideas here? So what would the dashed line represent? It's a simulated setting, so I know what the different components in my specification over here, what they are. So I also know what the, any ideas here? It's the lowest MSE possible. It's the variance of epsilon. Yes, very good, Jonathan. So we know that we can never get this test mean squared error below, it cannot go below the irreducible error, and this irreducible error is captured by the variability of the epsilon. And because this is a simulated setting, I know what this variability is, and I can picture it here on my graph. Of course, in reality, you wouldn't know what this dashed line would be, but in reality, you would hope to recognize this U shape when you are evaluating the test error or the test loss function for different levels of complexity or for different values of tuning parameters. Okay, this was an easy example. What about the next one? So here is the true F is again in black. I go for a linear regression in orange. I go for smoothing splines in blue and in green. Which model do you prefer? Any thoughts, any ideas, any suggestions? Which one do you prefer? Again, blue or blue-orange thoughts I get, right? Certainly not green, that's very good, Robin, sorry. Indeed, so we pick up the right ideas, so we would definitely not go for green, because green is again in the area where our test error is increasing. Will we go for orange or for blue? Well, that's of course a debate that you can have among different modelers, but our general principle is, of course, as Cedric indicates, Orange is the most simple, and we prefer simple models above complex models, right? So we prefer simple models that perform approximately as good as the more complex ones. So that would definitely be an argument to go for the orange model here, because you can say it's simple, it's just a linear regression model, and its performance is approximately as good as the performance of the blue one, which is the blue one, you could say it's really minimizing the test error, but the orange is so close, and it is more simple, so that would be a good reason to go for the orange one over here, right? And of course, we recognize again that the green model is pushing the training error lower and lower. But be careful, that's not a good reason. That would not be a valid reason to go for this green model, because you see what the green model is picking up in terms of trends in the data that is not transferable to what we see in the test data. All right. Last example, which one do you prefer here? Which one do you prefer? So I see blue popping up a couple of times. Yes, very good. So blue is minimizing my test error. It's more simple than the green model. So that would be a valid reason to go for the blue model over here. Why do we include this example? Because what you see here is that this U shape that we hope to recognize in the display of the mean squared error evaluated on test data. So this U shape, it's only kicking in very slowly, right? So it's not always apparent right away that the performance of your model will start to become worse, that the test error will start to increase again. So that U shape, it's not always easy to capture that or to recognize this behavior easily in your graph. So this is an example where the U shape starts to kick in only rather slowly. All right. So this was an important kind of thinking. We can do different levels of complexity with our model. We can picture the training error, we can picture the test error, and we would go for the level of complexity that minimizes this test error. Okay, so here you see a few more details about the reason why the test mean squared errors in these graphs were behaving the way that they behaved, right? So here we picture the bias variance trade-off for the three examples considered before. And again, this example is taken from the book An Introduction to Statistical Learning, so you can read about it in more detail in the book. But you see here the test mean squared error. You see here how the bias is behaving, how the variance is behaving. And if you add these two together, you'll recognize the behavior of our test mean squared error. So this really pictures this trade-off between bias and variance, and the way how they perform or their rate of change amongst each other, that's going to drive the particular shape of this test mean squared error. You also see that if we build more complex models, we'll be able to push the bias to zero, but the variance will start to increase, right? And so how they behave amongst each other, that is going to drive the shape of the test curve that we recognize here. Okay, so that's an important idea, this bias variance trade-off. All right. Now let's do one additional example. And instead of doing the regression setting that we covered in the three previous examples, we're now going to look into a classification setting, right? And so I'm going to try to predict the label associated with a target variable. And that label could be like default, non-default, fraudulent, non-fraudulent, things like that. And of course, if I want to evaluate the error of my what we call a classifier, so classification model, that's often called a classifier. If I want to evaluate the error that this classifier is making, then I can evaluate it on training data, I can evaluate that on test data. And what I'm actually going to do here with the measure that I propose over here is that I'm going to look for which observations is the original label, the y, different from the predicted label, that's the y hat, right? So whenever this condition is fulfilled, the indicator variable capital I here will throw a value equal to 1. So I'm going to count in a data set with n observations, how many errors do I make? And I'm going to count this number of errors. I'm going to divide by the size of my data set, and I'm going to call that my error rate. So the goal of a good classifier is, of course, to make this error rate small on test data. Okay. So we explained all of this. So this is the training error rate. If I generalize that to test error rates, then I'm going to look at new observations and I'm going to calculate what is the average number of errors that I'm going to make over there. So a good classifier is one for which the test error is small. Now let's look at a famous example of such a classifier. We're going to do the k nearest neighbor classifier, and we're going to play with the value of k. Okay, so that's going to be what this example is about, how to pick a meaningful value for this k. So with k nearest neighbors, you can use that idea for classification, as we're going to do in this example. You could also use it for regression, as you will see in other examples. So what is the idea? We pick a positive integer k. We're going to pick a test observation x naught, say, and we're going to identify the k points in the training data that are closest to x naught. And of course, this closest, you have to pick a distance measure to express this. You have to use Euclidean distance or some other kind of distance measure. So you have to pick a distance measure to express this. So here is the idea. If you pick, first of all, the k points that are closest to x naught, then you get a set with n naught observations. And in this set of observations that you identify, you're going to see which label is occurring most often in this set n naught. And the label that is occurring most often, well, that's the label that you're going to attribute with this k nearest neighbor classifier to your test observation x naught. So let's explain that with a picture that will be easier. So here's what I want to do. I've got a data set with labels, orange and blue. I identify k equals 3 in this example. So that means if I have to predict or if I have to attribute a label to a new observation identified here with the cross, then I'm going to look for the 3 observations in my data set, in my training data, which are closest to this observation identified here with the cross, right? So if I do that with Euclidean distance, I get the 3 observations identified here. I see that 2 of them are blue and 1 is orange. So the probability to allocate the blue label to this cross is 2 out of 3. The probability to attribute the orange label is 1 out of 3. So I'm going to say this new observation, I'm going to predict that it's going to be a blue observation, right? So that's how it works. And if I let the x move around in this frame, then I'll get a decision boundary that is visualized here with the black line. And I'll get everything colored here in blue will be predicted as blue. All colored in orange will be predicted as orange. Yeah. So here it's very simple because I have very few. I have a low-dimensional problem, so I can picture that with the graph over here. But that's the idea. So my first question for you is this a supervised or an unsupervised learning technique? So let's Shout in the chat. Is this supervised or unsupervised according to you? I've got a mixed set of opinions. I see some people saying it's unsupervised, and I see people saying it is supervised. And that's traditionally, if I ask this question, I get a mixed set of answers. Who wants to explain this? Somebody shouting supervised. Who wants to explain why it is indeed supervised? Because that's the correct answer. Anyone? Jill, you want to go? You want to help me a bit? So can you unmute your microphone?
Can you hear me, Professor?
Hey, Jill.
Hello. So you've got your training data, which has labels.
Yes.
A blue label or a red label. And so based on the labels, you decide the label of the new elements. So it's supervised.
Supervised learning. Very good. So we do indeed, we have a particular label for our data sets, for our data points. You're either orange or you're blue. So that is supervised learning. So it's a tricky question. And at first sight, you would say, it's unsupervised because of the way how it's pictured here. But don't, be careful about it. We use labeled data, orange, blue, fraud, non-fraud, default, non-default, etc. So this is indeed an example of supervised learning. All right, very good. Now we want to pick the level for K, right? So we want to decide which value the parameter K should take. And you see here that I plot three different K nearest neighbor classifiers. One where K is equal to 1, one where the K is equal to 10, and one where the K is equal to 100. And we see the constructed decision boundary that's in blue. And we also see this purple dashed line. You can forget about that, but that's the Bayesian decision boundary. You can compare that for the simulated data that we're working with here. You can compare that with the dashed line that we had in our regression example. So that is kind of the irreducible error that we're making, right? So that's the Bayes classifier or Bayes decision boundary. I didn't explain that, but you can look that up if you're interested in. So my question for you is simple. Which classifier do you prefer? Which classifier would you explain as underfitting? And which classifier would you explain as overfitting? So let us first hear which one, or if you type your answer, just say, okay, I prefer this one, the overfitting one, that's this one, the underfitting one, that is, what do you think? So I'll give you a minute to look at that. So answers start to pop up in the chat, and answers are quite mixed, which is a good thing. We have some debate. So keep in mind, overfitting means that you're picking up the trends in your training data at a too granular level, and you're picking up ideas that are not transferable to new data. And underfitting would mean that you are too crude, right? So that you are too rough. So I'll take Marco's answer here, because that is indeed the correct answer. So Marco says, I prefer the one where k is equal to 10. And I see the one where k is equal to 1 as overfitting, and k equals to 100 is underfitting. And that's indeed correct. So good job. Because we see, if we look at k equals 1, that we're really just replicating almost, or we're really picking up the trends in the training data at a too granular level. For instance, here, I've got a blue labeled observation in an island of orange, right? And the classifier is going to say, oh, I'm going to predict this as a blue one. But that's actually overfitting. That's like interpolating or replicating your data instead of picking up the general trends, the signal in the data that we try to capture. And if you think about it, what does it mean, k nearest neighbor? Where k is equal to 1, yeah, then you're just going to look at the observation that is closest to the new observation that you try to predict, and you're gonna take the label of that observation. If you do k equals to 1, k nearest neighbor on training data, and then that would mean that you build a classifier which has error 0 on the training data. So that is completely overfitting. So this one is overfitting. The other one here is too rough. So that one is underfitting because it doesn't, like here, it's not picking up the blue observations that you see over here. So this one is underfitting. The predictions that we get over here, they are too rough. And here with k equals 10, we get a classifier that is for which the decision boundary is also very close to the decision boundary of our base classifier, and we know that we can't do any better than that one. Of course, this is a simulated example, so we know where the purple dashed line will be, but in reality, of course, you don't know what that decision boundary would look like. Okay, so if I go a bit further on this, if I look at k equals 1, then my k nearest neighbor training error rate is 0, but the test error rate may be quite high, as I explained. With more flexible classification methods, our training error rate will decline, test error rate will not. How to pick a meaningful value of k? Well, what you're going to do is you're going to try out different values of k, and you're going to pick a value of k for which the test error is minimal or close to the minimal error rate. So in the plot on the next sheet, I'm going to picture this as a function of 1 over k, right? So 1 over k, that means if k is equal to 1, then 1 over k will also be equal to 1. Then I'm over here. Then my training error is 0, but my test error is starting to, is increasing again. Okay, so this is a model that is completely overfitting. If 1 over k goes to 0, it means that k becomes very large. And if k becomes very large, then it means for k nearest neighbor classification that you're basically going to use the whole data set and just see empirically how many times did I see the orange label, how many times did I see the blue label, and you're going to use these very rough probabilities over the whole data set available, right? So with 1 over k going to 0, you are underfitting. Which level of k will you pick? Well, you will pick a value for 1 over k, in this case, that is around these values. And you'll see that you have some freedom there to choose a value for k that makes sense. So we call the k here a tuning parameter. So it is a parameter in our classification model in this case, for which we need to pick a value, but we do not have an analytic expression for this parameter k. So the only way how we can decide about a meaningful value for this k is to try out a grid of different values of k, evaluate the test error, and then pick a value for k where this test error is minimal or close to the minimum. All right. Any questions on that? So that is an important way of thinking, which we like to use further on in the machine learning methods that we're gonna study. Any questions? This makes sense? Okay. Good. So Kevin, go ahead.
As can you show the graph again?
Yep.
Okay, so on this graph, you can, for instance, choose for any value where the orange curve kind of hits the dashed curve.
Yes.
But is this choosing done by the user of the program itself, or is it also done by the machine learning practice?
Say again the last part. I didn't understand.
So you're picking a value for k, but is the picking of the value itself done by the algorithm, or is it done by the person using or developing the algorithm?
Yes, very
like manually.
Yeah, so in the end, I would say it's always done by the person who calibrates the algorithm and has to make the final choices. But you will see that when we go to coding examples of these machine learning methods, you will see that often these techniques, if you look at their implementation in R or in Python or something, they have a built-in function that will tell you, okay, I'm going to do cross-validation and I'm going to give you back the value of the parameters for which this cross-validation error is minimal. Or they often also implement this one standard error rule, which I will explain later on. But then you pick a value for k, or for the tuning parameters, where you're close to the minimum, but you are a bit more conservative, let's say, and you allow for a certain deviation from this minimum. So both are possible. You could say, I'm looking at my implementation in R and in Python, and I'm going to ask this routine to give me these optimal values for the tuning parameters. But you could also say, I'm gonna look at graphs like this, and I'm gonna overrule this choice that was made by my implementation. Does that help
thanks.
or not?
Yeah, that helps. Thanks.
Yeah? But that will become clear if we look at implementations of these techniques. Okay. So what I want to do now is dive a bit more into what kind of different techniques will we see in the next classes, and how should we let's say classify these different techniques? What are the things we should keep in mind if we want to tune parameters and stuff like that? And again, I took this this picture here from the website Machine Learning for Everyone. I think it's a nice one to picture different classes of learning methods, if you want. So let's say a few words about these. So if you have simple data with clear features, you can go for classical machine learning or classical statistical learning. So that is linear regression, GLM, GAM, maybe a decision tree, stuff like that. Simple data, clear features, that means data like we've seen them so far. Nothing very special about that. Typical tabular data, structured data, simple data, right? On the other hand, if you say quality is a real problem, so you really want to improve your predictive accuracy, and you are looking for specific interactions between features, you can't do it with a simple machine learning or statistical learning model, then you can go for ensembles of models. So we'll see a few of these ensemble techniques. So that's thinking random forest, thinking gradient boosting. You could also look at techniques like stacking of different models to improve your predictive accuracy. On the other hand, if you say my data are very complicated, I have unclear features, think about unstructured data, think about images, think about text. I want to believe in a miracle, then you can go for techniques like neural networks, deep learning. Of course, this is a bit of a cartoon or karikaturale voorstelling in Dutch, but it's a good way, it's a good thing to keep in mind. And these ensemble methods, think gradient boosting, think stacking, for instance, and the neural networks, they are eternal competitors. Huh? So they are like gold standards in terms of predictive accuracy, which often compete with each other. On the other hand, there is this other field which we didn't talk about, but this is about what if we have no data, but we have an environment to interact with, then you have this class of reinforcement learning methods, but that's something I won't touch in this course. Okay, so what I want to address are a few general considerations about picking an appropriate technique for the data that you have at hand, picking the settings of tuning parameters, and so on and so forth. And then in the next classes after the Easter break, we will cover these different techniques in more detail, particularly with a focus on modeling frequency severity data for actuarial science. Right? So here is a brief overview. I won't say a lot about this. You can read about that. But if we go back to the 19th century, we entered the world of least squares linear regression. That was then extended to also analyzing, modeling qualitative values, classification problems, logistic regression in the 1940s. Then in the 1970s, the generalized linear model work came up. So we discussed that already extensively. We discussed the book of Mikulak and Nelder and the important concepts of these GLMs. Then in the 80s, Breiman and co-workers introduced classification and regression trees. So you may recognize here the acronym CART. So we're going to talk about that later on. So CART stands for classification and regression tree models, right? So that's everything that has to do with decision trees, regression trees. Then the generalized additive models, end of the 80s. And since that time, inspired by the advent of machine learning, we see that statistical learning and machine learning emerged as a field in statistics and in computer science. Okay, so that's a brief history with some timelines. We already encountered this graph in the first class, but I really want to show it again over here. So we have on the x-axis flexibility of the modeling technique. On the y-axis, we have interpretability. So if you look at low flexible models, they're typically highly interpretable. And you know you can do inference with these models. These are white box models. You understand how these models construct a predicted value for your target. If you look at more flexible models, then these are typically way less interpretable. Think boosting, think neural networks, but also keep in mind there is this new field, if you want, coming up about interpretable machine learning, which is showing us or bringing us tools like partial dependence plots, like ICEs, like other visualization tools that try to open up this black box and to make sense of the predictive models that we're constructing, right? So picking a trade-off or picking a level of flexibility and interpretability, that's going to be important. And we'll also see that, or we already discussed that for insurance companies, especially when you put up models that have to go to a regulator, that have to be reviewed by a regulator, then you want to have a certain level of interpretability. Then you want to open up the black box of the model that you will construct. Yeah, so way more about that later on, all right? We discussed overfitting already. We say, well, modern classification regression models, they're highly adaptable. They can easily overemphasize patterns which are not reproducible, so which are not reproducible from the training data to the test data. And the model we built should predict the test data, so new samples, with a similar degree of accuracy on the training data, okay? Now, the new idea or the new concept that I want to bring up over here is that many of these predictive modeling techniques have so-called tuning parameters or tuning hyperparameters, which enable the model to flex, to become more flexible, to find the structure in the data. And model tuning or parameter tuning is then the step we need to go through, or the process of using your available data to identify the appropriate settings for the model's parameters, right? So we want to use the settings that yield the best and most realistic predictive performance. So maybe a question for you, can you give an example of such a tuning parameter that we encountered so far? So who wants to go ahead? Who can give an example of a tuning parameter? No one there? So what would be an example that we discussed so far? So as Jill says, indeed, the K from our K nearest neighbor classifier. So K is a typical example of such a tuning parameter. We don't know how to pick the value of K a priori. We cannot estimate it analytically from our data, but we can evaluate the performance of different models constructed by picking different values of K, and we can go for a model that performs well on new data. Yeah, so that's the idea. So important is, and that's very hard for a traditionally trained statistician or mathematician, but there is no analytic formula to calculate an appropriate value for these tuning parameters. And typical examples are the K in the K nearest neighbor, the depth of a tree, the numbers of tree we're going to combine in an ensemble method, the cost parameter in a support vector machine, the shrinkage parameter in a gradient boosting machine, all of these kind of parameters. We need to pick meaningful values for them, and we do not have analytic formulas at our disposal. Yeah, so we want to design a sort of general strategy or recipe now I'm confused, of course. My oldest son is entering the room. It should have happened once, of course. So we want to come up with an applicable, with a recipe to pick these meaningful values for the tuning parameters. And for that, we're gonna use resampling methods. So that's what I want to discuss in the next sheets. Okay. So let's look at a general approach for searching for these best values of the tuning parameters. We're going to define a set of candidate values called a grid. Think about the grid of values for K that we evaluated. We're going to get reliable estimates of the model utility across these candidates. Think about building the K nearest neighbor classifier on the training data, and then using that to predict the test data, and then capturing or measuring the error made on the test data for each of the values of K that we investigated. That's what we're going to do. Then we're going to pick the optimal settings of our model. And then a last step, and I'll mention that right away, but the last step is that you then, with the optimal values of your tuning parameters, you're going to refit the model on all the available data for those particular values of the tuning parameters that you decided on, and you're going to use that model to deploy in practice. So I'm going to show this with a flow chart, which I took from the Kuhn and Johnson book about applied predictive modeling. So I like this visualization a lot. So try to understand what this flow chart is picturing. So we're thinking about machine learning methods, statistical learning methods, where we need to pick a value for certain tuning parameters or for a certain tuning parameter. And because you can have one such parameter, but you can also have multiple tuning parameters that you need to make a choice for. So what you're going to do is you're going to define a set of candidate values. So we often call that a grid. We're going to evaluate for each candidate set. We're going to resample the data. I'm going to explain how that works in the next sheets. We're going to fit the model on the training data, and we're going to predict the holdouts, right? So think about kind of test data if you want, right? Typically, we're going to do this multiple times. So we'll see that when we're explaining cross-validation, but we're going to repeat this recipe a couple of times, say 5 times or 10 times. And we're going to aggregate the resampling into a performance profile. So when you look at the error made when predicting the holdouts, if you do that 5 times or 10 times, you're going to average these performances here. That's what we mean with this block. You're going to aggregate the resampling into a performance profile. You're going to pick the final value, final tuning parameters. And using the final tuning parameters, you're going to refit your model with the entire data set that you have at your disposal. Yeah? So this is an important flowchart to understand at the end of today's session. This will also become more clear when we're actually going to work with these machine learning methods later on. Yeah? So the reason why we have to do this is because we have these tuning parameters in our model, and we don't know upfront how to pick meaningful values for them. We don't have an analytic formula for them, and we're going to rely on evaluation methods like this. Okay, so what do we still need to explain? We have to explain how this resampling goes and how this aggregation of the resampling into a performance profile, how that works, right? We already talked about how to pick the final tuning parameters. And I think the last block makes also sense. So once you decided upon the optimal value for your tuning parameters, you can refit the whole model with the entire training data. Okay, so we'll have to think about this block, how to do this. Okay, so we'll need trustworthy estimates of our model performance. We're going to test the model on samples not used for training. And on these samples, we're going to evaluate the set of candidate models defined by the tuning parameters. You can do that with a single test set, or you can do that with resampling the training set, evaluating the candidate models on these modified versions. So that's what I'm going to explain next. So how to work with these, with this resampling idea. Okay. Welcome back to the session. So we're gonna start again to discuss the final part of today's presentation. And I will pick it up again from sheet 40 from today's deck of lecture sheets. And what we want to discuss right now are different ways to resample your data such that you can use the available data to evaluate the performance of the models constructed under different settings, to evaluate their performance on data which have not been used during the training phase of the model, right? And you will see that in the literature on resampling techniques, there are a couple of things you should keep in mind. So I want to guide you through different ways to use the available data. And the first way to do this is what we call the validation set approach. So with the validation set approach, you're just going to split your available data in 2 parts. And you're going to say, okay, I'm going to use part of my data for training, and I'm going to use the part of the data that I didn't use for training. I'm going to use that to evaluate the test error rate. And typically we can say 70% is used for training, 30% for test, or 80% for training, 20% for test, things like that. Okay, so we call that the validation set approach. And I'm going to illustrate these different concepts here with an example, again, taken from the book, An Introduction to Statistical Learning. And what we're going to do is we're going to use the famous MPG data in R, and we're going to model this MPG target variable as a polynomial function of horsepower. So it doesn't matter too much what this data is about, but you've got a target Y, you've got a covariate X that you want to use, and you want to decide, should I go for just X in my regression model, or X and X squared, or X squared, X to the power 3, and so on and so forth. So the question here is how to decide upon the degree of the polynomial of horsepower that we want to use, okay? And what we're illustrating here is this validation approach, where we say, let's use, for instance, 70% of our data for training and put 30% aside as a validation set. And let's calculate the mean squared error over this 30% of the data that we didn't use for training. And let's do this for different degrees of the polynomial of horsepower that we want to do, right? So here on this graph, I do this for just one split of the data into training and validation set. And here I repeat this exercise if we do this multiple times. So what you'll see here, and that's the second bullet on this sheet, is that this validation estimate of your test error rate can be quite variable, right? Depending on how you do the splitting into 70% of training, 30% of validation data. Question for you, which degree of the polynomial would you use? So even though these curves are pretty variable, they seem to lead to a consistent choice of the degree of the polynomial. So which one would you prefer? So Said says 6 should be okay. Any other thoughts or any other ideas? Which degree of the polynomial would you use here if you look at these kind of curves? 2 is enough, indeed. And the reasoning is quite similar. So you shouldn't look for like the minimum of the performance here in terms of the mean squared error. But what you see, what the general trend is that you get out of this is that you get a very sharp decrease in the test error if you go from polynomial degree 1 to 2, but that from there on there is kind of this hockey stick behavior. From here on, the curve stays rather flat, even though there is still a bit of fluctuation over here. But you see that you won't be able to push the test error rate really substantially lower. So then again, we prefer to go for a less complex model. So we prefer to go for the simplest possible model that achieves a reasonable level of performance. And in this case, we would indeed go for a degree of the polynomial equal to 2, right? So this is the first thing we can do. The next thing I want to mention here is the leave one out cross-validation, which you probably have heard about in a more traditional statistics course. So leave one out cross-validation is going to split your available data into 2 parts. You're going to use a single observation for validation, so to evaluate the validation error, and you're going to use the rest of the data to make up the training set, right? So that's, as the name says, you leave one out, you leave one observation out of the available data, and you're going to evaluate the performance of your model on this single observation. Now, if you train the model on this data from X2 or from observation 2 to observation 1, then you construct a predictor, a predictive model, and you can use this predictive model to establish a prediction for the Y1. So you get a Y hat 1. So you can calculate the mean squared error, or whichever type of loss function you want to use, on this single observation. And what you'll get here is an unbiased, but a very highly variable estimate for your test error. So what we're going to do here is we're going to repeat this procedure and leave each of the available observations in our training set, leave each of them out once, calculate the n mean squared errors, and take the average over all these n steps. And that's what we'll call the leave one out cross-validation estimate for our test mean squared error, right? So here, by resampling our original data, our training data, we get an estimate that is a reliable estimate for the true test mean squared error. So if I picture this, you'll get a procedure like this. So you have a training data set with n observations. You leave one of them out in each step. So that's indicated here with the orange. You build the data on the available blue observations. You use it to predict the orange observation. You calculate the error rate, and you're going to average that over these n steps that you see pictured over here, right? So this creates an estimate for your test error, which has less bias, which is also less variable than the validation set approach that we discussed earlier on. But this is, of course, very expensive to implement because you'll essentially have to run the model n times. So if you do a complicated model with a lot of features, this would be a no-go because this would really cost you too much time to implement. We'll see the picture of this leave one out cross-validation evaluated on the MPG target variable later on. But let's immediately jump to a third possible strategy. And that is the one we're going to use a lot throughout the course and which is used a lot in machine learning settings. That's the k-fold cross-validation. So what we're going to do is we're going to divide the set of training data into k groups or folds of approximately equal size. We're going to treat the first fold as our validation set. We're going to calibrate the model on the remaining k-1 folds. And we're going to use the model built on these k-1 folds to predict the observations in the first fold. And that's going to create our mean squared error, or our loss function, evaluated on the first fold, right? We repeat this procedure k times, and we take the average of the constructed, of the calculated error rates. And that's what we call the k-fold cross-validation estimate. Yeah, so do keep in mind, this is an average over k mean squared errors that you calculated. And this k, that's the number of folds you're willing to construct. And typically we take the value of 5 or 10 for this k-fold cross-validation. So if we picture it, you'll get something like this. So you take the available training data. You're gonna split the data into k folds. You're gonna train the model on the blue data, and you're gonna use it to predict the orange data. And you're gonna do this in this example 5 times. So you get 5 mean squared errors. You're gonna average these 5 values, and that's gonna be your 5-fold cross-validation error. So that's what we wanna do in the k-fold cross-validation. If I picture that, let me jump right away to this one. If I picture that on the example that we discussed earlier on, then you'll see here, if I let the degree of the polynomial change, this is my leave one out cross-validation. So this is this super computationally expensive way to estimate, to approximate the test error, right? And here you get the 10-fold cross validation. Now, of course, I can construct different, I can repeat this 10-fold cross validation calculation. So that is what the different lines here in the graph represent. So what if we put the data, the training data in 10 folds, approximately the same size, but we could, of course, repeat this experiment. And that's why you get these different lines over here. This is just to illustrate that this is going to give me a quite stable performance curve, right? So here you see, in contrast to the validation set approach, that there is not much variability in the estimates that I get for my mean squared error curve over here. And you also see that it's pretty close to the leave one out cross validation that we show over here. Maybe one extra word about this leave one out cross validation. So you may have seen this in a discussion of linear regression, generalized linear regression in other courses, because for certain rather simple methods, it turns out that we can have analytic expressions for this leave one out cross-validation. And then, of course, you can quickly evaluate it. But in general, if we step towards these machine learning methods where there are a lot of parameters to be tuned, then this approach is a no-go zone because it would be computationally too heavy. Of course, my question for you is, which degree of the polynomial would you go for? And again, I think you can be quick about that in the chat, but again, we see that degree 2 makes a lot of sense here. It's the simplest model. From here on, the curve stabilizes. We recognize this hockey stick behavior, and this is in line. So we get the same conclusion here across the different ways of calculating the mean squared error that we discussed. Yeah, whether you go for the validation approach, the leave one out cross-validation, or the tenfold cross-validation, they led us to the same conclusion here. But keep in mind, validation set strategy leads to quite a lot of variability in your test or in your validation mean squared error curves. Tenfold cross-validation, fivefold cross-validation, that's usually a better idea, right? Okay, let me just show you one additional picture, which I think is a nice one. I took this one from the book by Boomke and Greenwell on hands-on machine learning with R, which is a very nice book, came out in December 2019. So we're gonna use more illustrations from this book later on in the course, but I think it's, personally, I think it's a very nice book. And here you'll see if I have my training data available, yeah, I'm gonna put my data into 5 folds. Okay, so that's, or I'm gonna organize 5 folds if I wanna do 5-fold cross-validation. And what I'm gonna do per fold is that I use part of my data for training the model, and I use the remaining part of the data to test. Okay, so what I got here is per fold, I've got a performance measure, fold 1 performance, fold 2 performance, and so on. And in the end, I'm going to calculate the average performance. Yeah. Now, in terms of the terminology, I think there are 2 ways how authors use this term fold. So you could say the folds, that's really the 5 groups that I make and that I'm going to combine in a certain way when training the model and evaluating the model. But sometimes authors also refer to the fold as the particular way how you're gonna organize your training data into train versus test. So here, fold 1 refers to organizing the data like this. And these 5 blocks refer to the 5 subgroups that I made out of my original available training data. So sometimes it's a bit confusing at what others really mean with the fold. Is it one of these blocks, or is it just the way how I organize the data that I put together, that I divided into separate blocks, the way how I put these together. So the term fold is used for both of them. Okay, I guess that's what I wanted to say. A few extra words, and that is about cross-validation, but cross-validation with a little twist. And this is also what we're going to use later on typically, and this is called stratified k-fold cross-validation. So I want to name it at this point. We'll see it coming back later on when we're actually going to do like gradient boosting for claim frequency, etc. But sometimes, if you look at the k-folds that you construct, so if you put your data into k-folds, your training data into k-folds, here labeled as D1 up to dk, being disjoint random subsets of approximately the same size, Then, of course, because you do this randomly, it could happen that outliers may fall into the same fault decay, and that this substantially distorts or disturbs the k-fold cross-validation. So think about your claim frequency example with the MTPL data that we discussed about up to now. Well, what could happen if I organize this MTPL data in 5 groups is it could happen that I put all the people who report 4 claims, 5 claims, that I put them together in the same fold. Then that will be a fold which looks quite different from the other folds, right? And what I will see then is that this really may disturb my performance evaluation, because I have this fold then where I put the outliers and the very high risks all together, whereas in the other folds I don't have observations of that kind. Yeah, so that is a reason why sometimes researchers say I want to avoid this, and I want to do stratified k-fold cross-validation so that I get a more equal distribution of my outliers over the different folds. And so then it means that you're gonna look at, let's say in the example of the claim frequency, you're gonna look at the people who report a lot of claims, and you're gonna distribute them equally across the different folds to avoid that there is a single fold which contains all these outlying observations. Yeah, and if you think about how to organize this, well, you could put it like this. Huh? You could say, I'm going to look at my target variables. I'm going to order them from large to small. Yeah, that's what you see over here. So I'm going to use this one for the maximum, and I'm going to use this one for the minimum. And I'm going to say I'm going to build folds or groups such that U1 contains the k largest observations in my data set, U2 then the next k largest observations, and so on. So these U's, I've got n divided by k of them in total, and each of them contains approximately k observations. And then when I actually construct my folds for k-fold cross-validation, I'm going to pick randomly from each urn. So I'm going to pick an observation from U1, then an observation from U2, and that's how I'm going to continue. So this avoids that in this way, I can never put all the large observations or all the small observations in the same fold. So this would be a possible implementation for this stratified k-fold cross-validation. Yeah. This also has a connection to what Kevin asked earlier on, like how are you going to put these training and test set together? So you could also use this kind of idea to do that. At this point, I'm going to make a small excursion to a sheet that I covered earlier on. So apologies for that, but I want to show you again the graph or the visual that we discussed here, right? So what you will see here now, this is one that we discussed earlier on. And at this point, you should now be more capable of understanding this scheme, right? Because what we say here is that once we have all the available data, we're going to put a part of them under lock, and we're going to call that the test data. We're not going to touch them until the very, very final step of our process. That is to evaluate the performance of the model across different models to compare performances on the test data. And then the techniques that we discussed up to now, they fit within the blue area of this curve, right? So they tell us how to use training validation, how to do cross-validation, and typically we're going to do this blue, or the steps in this related to this blue part of my data. We're going to use that to tune the model parameters. right? So we're going to use either this training and validation strategy, or we're I think we lost the connection for a moment. Is it okay? Are we back again?
I am back again, but I indeed had some problems with the connection.
Ah, it's the
Yes, and
second
for me.
time. Okay, sorry. Yeah, it just, I think it's the Zoom that lost connection for a moment. So everybody's back. So I'm gonna pick it up from this picture again. Is that good? Or at which point did we lose the connection?
For me, it was at this point, so I was still following here.
Okay. So let's pick it up from here again. That's okay for everybody? Right. That's okay. Good. So what I was about to say here is, if we look at this scheme, I think it's useful to look back at this graph now that we understand what k-fold cross-validation and so on is. So a typical approach that we take is we take all the available data, we put part of it aside as test data. So that could be 10%, could be 20%, whatever. We put these on the log. We're not going to touch these during the training phase, the model building phase. Yeah? How are we going to do this model building? Well, think about the tuning parameters. You have to pick meaningful values for the tuning parameters. How are you going to do that? You can do that with a training validation approach. You can do that with a k-fold cross-validation approach, right? So then you're going to use the part of the data in blue. You're going to apply cross-validation to it, and you're going to use that to pick the values of your tuning parameters. Once you have these meaningful values of your tuning parameters, you can recalibrate the model on the part of the data that is available in blue, and you can then evaluate the performance of your model on the red block of data. And you can do this for different models, right? You can try a gradient boosting, you can try a neural network, you can try GLM, you can build them in the appropriate way with the data in blue and evaluate all of them on the data in red to compare the performance of different models. So that's an experiment that is typically set up, and where a lot of these resampling and evaluation ideas come together. Yeah? So it's important that you keep this, this picture in mind, because you'll see that kind of thinking coming back later on in the course. Any ideas or any thoughts, questions about this? It's clear? Yeah, so it puts a couple of things together, right? It talks about these test data, and then here within the training data, I can apply preferably, say, k-fold cross-validation to tune my parameters to make decisions about my model settings. Once I took these decisions, I'm going to recalibrate my model on the whole blue set and use it to predict the data in the red block. Yeah, so that's what I wanted to say over here. Okay, so let's jump back to the final steps that I still need to discuss. So we're here then. What you can see here is we return to the examples discussed earlier on. The example with the black curve, the orange curve, the blue one, and the green one. And what you can see over here is the true test mean squared error, that's in blue. Why do I know that here? Because we work with simulated data. So we can always simulate new data as a test set. So we know what this true test mean squared error would look like. Then you'll see the leave one out cross-validation in black, and you'll see the 10-fold cross-validation error in orange, right? So you'll see that or the main conclusions here, that if you look for the location of the minimum of the test mean squared error as evaluated, leave one out cross-validation or tenfold cross-validation. So this minimum, it's not exactly the same, but it's close to each other, and it's also close to what, or it's in line with what the minimum would be of the true test mean squared error. Yeah, so these are the three examples we discussed earlier on with these different true curve f, and here you see how these, for instance, the tenfold cross-validation would approximate the unknown true mean squared error, which is known here because it's a simulated experiment. Does that make sense? So the conclusion is here that the level of flexibility that we would pick by using, for instance, a tenfold cross-validation, that it's quite in line with the result we would get if we would go for the leave one out cross-validation, and that is also in line with what the true test mean squared error would lead to. Okay, questions? So Claudio asks, is there a method which uses past k-fold choosing methods performance to predict the best criteria to apply for a new data set with the same features? So if I understand this question correctly, is that if you have a data set at this point and you build your model, etc., and then somehow a new data set, new data come in, think about you're following a portfolio of policyholders and you have them now during a certain observation period, you build a model for them now, and then a new year of data comes in. So new data come in, which might look pretty similar, but still it's new data. So I guess your question is about, can you generalize the conclusions that you have for the data so far? Can you generalize them to this new data if they have similar behavior? Well, I would be very careful with that, because you can never be sure that this new data that comes in, that it exactly has the same kind of features, the same kind of trends as the data that you already have. So whenever you have a substantial amount of new data coming in, my general recommendation would be to train the model again and to make your choices, or to validate your choices again. Does that help, Claudio? Okay, and then Ahmed has a question: how would we deal with missing values in the k-fold cross-validation? Yes, good point. So then it depends whether you're going to talk about missing values in the features or missing values in the target variables. So if you have missing values in the features, then you would either, I mean, that would be part of your pre-processing steps. So either you're going to say, I'm going to impute values for these missing values in my features, and I'm going to impute using, there's a whole literature there on missing value imputation techniques. So you could take an approach from there, or you're going to treat the X, so the feature with, when it has a missing value, you're going to treat that as a separate level or a separate category in your feature X. So that's also been done sometimes. Yeah. If your target variable is missing, then you cannot, well, you could impute again. You could also impute the label with missing value imputation techniques, or you could say, I'm going to ignore this observation and not use it because I didn't see the target. Yeah. So here the question, I mean, it's a very broad question. There's a lot to say about that. If time allows, maybe we'll see a few words about pre-processing steps, and handling with the missing values would be definitely part of your pre-processing steps. Okay, Ahmed? All right. So the last example that I want to give about these resampling techniques is just to name the bootstrap quickly. We don't need it, well, no, we do need this bootstrap if we're going to talk about bagging methods. And we'll also need this bootstrap way of thinking when we're going to talk about claims reserving techniques, right? So what are we going to do? We're going to create artificial data sets, distinct data sets, by repeatedly sampling observations from the original data set with replacement. So that is important. We're going to do this with replacement, and we're going to then use the replicated data to estimate the thing we're interested in, or to perform the calculation of interest. So for instance, in a claims reserving exercise, you're going to use these artificial replicated data sets to calculate your reserve once again, to get a whole distribution of outcomes for your reserve. So here's what's happening. We take the data set over here. This is a toy data set with only 3 records. And I'm gonna create bootstrap copies from this data set. So I'm gonna do this with resampling. And how do you see that this is done with resampling? Because for instance, record 3 here is popping up twice in my bootstrap copy Z1, right? So this is a bootstrap copy of my original data set. Here I've got another bootstrap copy, here is another one, and so on and so forth. And what these arrows here indicate is that I can then calculate the thing I'm interested in. In this case, it would be a parameter in a statistical model. I could calibrate my parameters on the available bootstrap copy. I can do that V times, and I'll get a view on what these parameter values could be like. So in traditional actuarial modeling, in traditional statistical modeling, this would be a way to get a grip on the variability, the uncertainty in parameter estimates, in cases where I cannot do that analytically. So in cases where I cannot analytically calculate the standard error or the variability of my parameter estimates. So we're going to come back to that. Keep in mind that this bootstrap idea is also a relevant resampling method to be used in certain applications. Okay, so that brings me to the end of today's class. So there are a few extra things that I want to say here in the final set of sheets. Yes, Jonathan, go ahead.
So my question was about bootstrapping. Doesn't bootstrapping lead to a form of a fitting in a way? By reusing again and again the data that is given from the start?
Yes, but how to see this? Because at this point, we don't want to use these predictions on the different copies to so what we're going to do here is we're going to typically average these predictions obtained, or these parameter estimates obtained over different bootstrap copies. And then what we're going to the kind of thinking we're going to apply is that if you take the variance of the sum, that by increasing the number of terms, the variance of the average, that if you increase the number of terms in your average, you're able to deduce this variability. Yeah, so we're going to apply this bootstrap thinking in machine learning prediction to reduce variability in our predictions. And we're going to use it in more statistical thinking to get a grip on parameter uncertainty. So I guess these are different goals that we try to achieve here. So we're not like if I do this here for claims reserving, then that would just be a way to get a grip on the parameter uncertainty that is present in the models that I built. So I don't, it's not like yeah, overfitting my data. I just use it in a different way with a different goal. But so my answer is not quite convincing, I realize, but let me come back to that when we're gonna discuss the use of these bootstrap copies in more detail later on. Because we're either gonna do it for variance reduction, or we're gonna do this to bring or to get a grip on this parameter and uncertainty. Yeah, but good point. Yeah. Okay. One thing I want to address here is something I already mentioned a couple of times, is this one standard error rule. So what is that in the machine learning literature? So here is what we want to do. We want to pick the final settings of our model. Now we want to pick a tuning parameter or something like that by quantifying the model performance across a grid of possible tuning parameters. And we want to pick the settings which are associated with the numerically best performing estimate. So what we did so far is we're going to look at the minimum of our cross-validated test error or something, right? And in general, we said we prefer simpler models above more complex. We already discussed that. So what you can do is you can either pick the tuning parameters based on the numerically optimal value, right? But that may lead you to a model that is a bit too complex. So what people often do is they pick a model that is more simple, but that is within a certain tolerance of the numerically best value. And that's what we call the one standard error rule. And it's a bit difficult to describe that in words, but I included a picture which I made myself, where I'm gonna play with the parameter k in a k nearest neighbor regression. And I'm gonna evaluate the performance of my model with 5-fold cross-validation or something, I don't remember exactly. And if I would go for really the minimum value, then I would get the yellow dot over here. So this is, let's say, 5-fold cross-validation evaluated for this k nearest neighbor regression, where I play with the value of k. Now, of course, in the curves that we've seen so far, we always represented this cross-validation error with a single dot or with a single point, because we say it's the average then over these 5 folds or over these 10 folds, and over and you look at the mean squared errors that you get for these different folds, you average them, and that's what you plot over here. But of course, because you have 5 numbers there, 10 numbers of which you calculate the average, you could also calculate the standard deviation of these 5 numbers or these 10 numbers. And that is pictured here with these bands where we add plus minus 1 standard error. Okay? So once again, if I do 5-fold, if I do 10-fold, I get 5 mean squared errors, or I get 10 mean squared errors. So I've got 5 numbers, I've got 10 numbers. I can calculate their average, but I can also calculate their standard deviation. And what we're then going to do with this one standard error rule is we're going to look at the minimum, we're going to look at plus 1 standard error, and we're going to put a horizontal line here. So that's what I did. I looked for the minimum, looked for what if I add the corresponding standard deviation, put a horizontal line here, and now I'm going to go for the less complex model, so for the most simple model that is within 1 standard deviation of the numerical optimum, right? So that means that I'm going to increase the value of k in k nearest neighbor, because then I make the model less complex. I mean, I make it more stable or less overfitting, if you want. And so the value of k that still fits within this one standard error rule would be the yellow dot that you see over here. So this gives me a rule of thumb to pick a value for my tuning parameter, the k in this case, which is within an acceptable range, if you want, of performance of the numerical optimum. So that's what we mean with this one standard error rule. This is also like a criterion that is often built in implementations of machine learning methods in R or in Python, where these routines will give you back the value of the tuning parameters based on the numerical optimum, but will also give you back the results of your tuning parameters if you apply this one standard error rule. So this comes back to Kevin's question earlier on. So these two yellow dots that we see over here would typically be given back by the implementation of one of these techniques involving tuning parameters in software implementation. So let me end. So choosing between multiple models then. So this would mean if I have a problem, I tackle it with a GLM, I tackle it with a gradient boosting. Then of course I can build my models, I can tune my parameters, and I can look at my test data, the ones I put under lock, and evaluate the performance of these models on the test data and make a comparison between different models and pick the model that would lead me there to the best performance. Yeah. What I just want to show here, and it's a bit early in the course perhaps to discuss this, but one way to finalize or to decide upon which model you want to go for. This is a recipe that I took from the book of Kuhn and Johnson, and I think it makes a lot of sense. So what you can do, of course, is you can start in general with several models which are least interpretable and most flexible. So you can put like a standard, like going for a gradient boosting or going for a neural network, perhaps. So among many domains documented in the machine learning method, machine learning literature, these models have a high likelihood of producing optimal results. So they can be treated as like a gold standard. They achieve good predictive accuracy. And then of course, what you can try to do is you can investigate simpler models. Think GLM, think GAM or something, which you can build using the insights that you obtain from these more complex models. And you could try to go for the simplest model that then reasonably approximates the performance of the more complex models. So we'll see how to do this in our claim frequency examples, where we could say, okay, well, in fact, we already did that to a certain extent in the pricing workshop that we discussed earlier on. There we went for a more flexible model, that was the GAM. And then we try to approximate it with a GLM. So we try to sort of translate the insights obtained with the GAM into a more simpler model. So you can also extend that kind of thinking, where you say, I'm going to start with a very flexible model that is known in the literature to typically lead to a good predictive accuracy. Think of a boosting machine or something. And then I can try to get the insights from that model being captured by more simple models. And of course, you would only do this if there is really a necessity to go for more interpretable models. But in an insurance context, that typically might be the case. Think about pricing. You have to explain that to different stakeholders, how you construct these pricing models. So there might be a value in approximating your more complex models with more simple models. Yeah. So this is an idea we'll see coming back again later on in the course, but do keep in mind that the fact that we constructed our GLMs as an approximation of our GAMs earlier on, that would be an example of this recipe that I tried to explain on this sheet. Okay. I'm going to end with this table of models from Kuhn and Johnson. I think we encountered this table already in the first class. So you see a lot of different models here. You'll see here an indication of whether the model is interpretable or less interpretable. And you also see an indication of the number of tuning parameters that your model is including, right? So we see, for instance, with linear regression, 0 tuning parameters, because there the parameters can analytically be estimated. We have an analytic expression for our estimators. If we look at k nearest neighbors, we have one tuning parameter. So after today's class, you understand where this one is coming from. If we look at more complex techniques like random forest boosted trees, you will also see that there might be a bit of discussion about the number of tuning parameters here. Well, that has to do with Jonathan's question, because sometimes some authors will tune certain parameters while other authors will say, I'm going to fix this to some predetermined values and I'm not going to do any tuning there. So you'll see that there is some freedom in the way how you're going to treat these models. Okay.